Hello and welcome to chapter 3. Today we will begin in this video the measures of central tendency and measures of dispersion. So in this first video on chapter 3, we will focus on measures of central tendency. Measures of central tendency really focus on the calculation of mean, median, and mode, and ways to do such certain problems that we're going to take up in this chapter. So like the weighted mean. So I'll first write down these things that I just talked about. These are often used in statistics loosely. Measures of the word itself, the phrase itself almost sounds like kind of the mean or coming towards where we are trying to find out the middle ranking as we do in the median. So we will go over mean, and then we will cover median. We sometimes take the median and not the mean, and then the mode. We'll work on some problems out here, so we can take up the measures of dispersion in a separate video. So starting with our mean. When we do mean, before that, we have to just know a little bit, just a little bit, so that we are going to use this for the rest of our course. There are certain things we covered from chapter 1, which dealt with the population versus the sample. And in chapter 1, we kind of elaborated on why we consider sometimes a population and why we sometimes consider a sample. Now, when we talk about a population, we usually use the first parameter. When we do a sample, or we take the mean of a sample, we say it's a sample statistic. In this chapter, we are going to have two different notations for a population mean. When we do the variance examples, we will see that there are two different notations for the population mean and the sample mean. Sorry about that. The population mean will actually have PowerPoint presentation suddenly throws off here. I'll try to share it again with you all. The population mean will be a parameter, whereas the sample mean will be a statistic. One will be mu, one will be s. So we will be doing problems based on this distinction. But let's go back to our actual lecture here, which deals with the measures of central tendency. The arithmetic mean is the most popular. You guys all know how to do it. I'm not going to show you how to take an average of a number. In fact, it will be fun to do it in Excel, where we will actually use the notation equals average, but we all know how to calculate the arithmetic mean. But there are certain characteristics of the mean that would be important for our knowledge. Remember, in levels of measurement, chapter 1, we talked about the ratio scale and the interval scale. So the mean would fall into either group: age, weight, height, etc. Almost all of them are ratio scale. Sometimes weight and height can also be measured in an interval scale. The major characteristics of mean: it is a unique value where you take all the observations. So be it the population we knew that we are going to calculate, or the sample statistic, the sample mean S that we are going to calculate, and all these calculations we will show in Excel, we will see that we have taken all the values or all the observations that are given to us. We know how to do the arithmetic mean or any other mean. We take the sum of the values, divide them by the number of values or the number of observations. I use the word number of observations a lot. Ladies and gentlemen, the data itself is the number of observations, how many data points you have. One interesting thing, probably you may not have thought about the mean, is how the mean, the sum of the deviations is zero. When a deviation is zero, what do I mean by this? Let's just take a hypothetical example. I was thinking about a good hypothetical example. I wrote these numbers, just four little numbers, or four little numbers here. So these will be 10 plus 4, 14, 19, 20. So sum 20. What is the mean? The arithmetic mean or any kind, I mean, we are not going into the weighted mean until now. So if you just take the arithmetic mean, it will be a 20 divided by 4, which is 5. So what is the sum of the deviations? The sum of the deviations will be the value x. We'll use this also in this version, the value x, which will be 1, 10, 4, 5, whatever it is, minus the mean, which is here. That's the mean. So it will be, so if you see the total deviation, all these, you will see 1 minus 5 plus 10 minus 5. So this is called the deviation, the value minus the mean, which you just computed, plus 4 minus the mean. I deliberately took a round example, rounded number, which will fall very easily into what we want to show here. So this is negative 4 plus 5 plus minus a negative 1 plus 0. So 5 minus 5 equals 6. So every time you do something like this, be it a fractional average or something, the mean deviations are always going to be 0. So another thing about mean is we can easily do the arithmetic mean, but you know, like these, it is a population mean, population divided by the number of observations, or we can get the sample mean, the sample divided by the number of observations, but it would be interesting to see how the data are weighted. But before that, let's just look and focus a little bit on these notations, because the notations seem to be very important in the statistics. In fact, in Blackboard, where I gave you those notes and handouts, in the notes and handouts tab, I have too many notes on how you are doing each problem step by step. So when you go to chapter 3, you will see I've made these notations very clear. The capital N stands for the population number of observations, values in the population. Okay, so remember the distinction between population and sample. If you do have access to all the scores of students in business statistics in Northeastern State University, you are looking at the population of the students. If you are looking at all the finance majors at Northeastern State University, you're looking at the population of students. So N represents the number of students in that population. The Greek letter mu is a very good way of representing. It has been traditionally used to represent the mean, the population mean. Sigma x, the sum of the values. So we know that we always take the sum. Sigma in Greek letter notation stands for sum. So we take the sum and divide it by the number of observations. I'm not going through all these problems. We can do these. You have to do tediously a summation and divide it by the number of observations. And you do the same thing for the sample mean, except please remember there are two distinctions here, ladies and gentlemen. Since I cannot take the notation on the Zoom whiteboard, I can use it in Excel. I'll just call it mu. Mu equals values divided by number of observations. Whereas sample mean plain English I'm writing, so if you're confused, you can go back to my notes. If you're confused, what was mu? What was the Greek letter mu? Sample mean equals, we call it S, sample statistic S, sample mean X bar. So we call it X bar here in this chapter. There's a different name in another chapter. We use the S as the sample statistic and use S as a standard deviation and all these for the sample. So X bar equals sum of values divided by, actually, observations, population, you usually denote it by n, whereas number of observations in sample equals 1. As I will said a little while ago, that in statistics, this notation seem to be very interesting, and if you can kind of don't have to by heart them, but if you can just kind of get conversant with them in each chapter, it's good that n represents the number of observations in the same in the population, and small n will represent number of observations in the sample. Anyways, the point I was trying to make is doing these arithmetic means like for ungrouped data. I mean, it's not grouped as yet. It's not very difficult. You just take the sum of the values and divide it by the number of observations in each case. But what is more interesting would be looking at the weighted mean. Okay, this is where we will dwell on some more problems. The weighted mean, why do we do this? The history is a little bit interesting because it can start with our census data, for example. Lots of people live in the United States, and if you think about household income or household who lives in the household and stuff like these, there are lots of variation, and we are going to take these up all in measures of dispersion also, and also when we do median. But one of the things that has happened in the past is when you take a data from census and use it for your population, or you are trying to look at the census data and trying to match up a sample that you are going to draw from one of the populations in the census. So for example, you want to draw a sample of people from Oklahoma or any other state, you are actually looking at people who may have high level of income in one direction, people who may have a lower level of income in one direction. You have sampled all kinds of people. Or there might be some people who are more senior in one sample, senior level people, and there's some people who are more young people in one sample. So when you are looking at random samples, this becomes sometimes a problem, and this is a sampling problem too with many researchers. So when you do the analysis, though, you have to be careful. If you have sampled too many people or too many households with a high level of income, your arithmetic mean will not give you the true average value of income. So you have to see you have to take the weighted average, the weights mean that those people who have the heavily weighted income, and then you have another group who has a low level income, give a higher weight to them. So you see, in that way, your mean becomes a true representation of the mean, because you have these heavily weighted income people, and then you have some people who do not have that much income level. So when you're taking your random sample, give a lower weight to the first class and a higher weight to the second class. It's things like this. A nice problem would be this. So a kind of problem I just explained. There are 26 hourly employees working in this construction company, 14 of whom are paid the lower level of wages per hour, whereas actually 2 of them are getting the $25 per hour. Okay, so again, the weightage is important. If you just take the simple value of these and divide by the number of employees, what will not reflect is an actual company level average mean or average or mean wage per hour. What it will reflect is just something that probably the two employees are getting more, because 25 is so much compared to 16.50. 19 is in between. So what do? We can do a clear weightage here depending upon what each employees are earning. So if you have 26 employees, you have 14 earning these, 10 earning these, and 2 earning these. So you take a mean weighted average, or a weighted average instead of a plain average of 16.50 plus 19 plus 25 divided by 26. You actually divide by the weights, the employees of the respective weights, and then you get this number. You can round it up saying that, well, the average the mean wage per hour in this construction company is $18.11. Before I go here, I'll stop here a little bit and go over some problems on this weighted average, which I have already done for you from chapter 3, and I will show you problems here for clarification. So Springer's is a company, and again, these are taken from your textbook. Springer's is a company which is selling 95 Antonelli men's suits. It's a brand for the regular price of $400. We know that these, if you are really looking at the branded men's suits, $400 is actually cheap. For the spring sale, though, the suits were reduced to $200 and 126 suits were sold. At the final clearance, the price was reduced to 100 and the remaining 79 suits were sold. So this is an interesting problem. If you think like that, if you check again the mean, you are not taking into account how the prices were at each clearance value. So if you think about the weighted mean price, if this is a problem in the exam, you know clearly that some suits were sold at 400, but then when the final clearance at half the price, and then 79 was sold at 1/4 the price, right? So you must take the 95 as its face value and then think about how many were sold here at the lesser reduced spring value. So these weights, and I already put the math equation there, I'm not going to mess with that. These weights are nothing but the 95 plus the 126 suits plus the 79 suits, and the weighted average that was equal to the 300 you just saw, and the weighted average, if you do the calculation, seems to be 237. The neat part of the problem is also here, number B. Springers pay 200 a suit for the 300 suits. Comment on the store's profit per suit if the salesperson receives a $25 commission for each one sold. So what would be the total cost given the salesperson's commission? It would be the $200 plus the $25 commission, so $225, the whole cost for selling it, and then the profit would be the weighted average minus the 225. The weighted average has actually given you the real estimated mean price. If you had not taken the weighted average and just got 400 plus 200 plus 100, you would have put a misrepresentation of the average price and you would have made a wrong calculation here. So $12 per suit was the profit meant. And then the same weighted average problems applied in question 2 and 3. The Alliance Healthcare System employs 200 people on the nursing staff, and the nurses aides, and these are nurses aides, receive 8 hours, while the registered nurses are receiving $24 per hour. Here is a clear-cut case of weighted mean, even if I don't ask you. You see the difference. Some are the nurses aides receive very low wage per hour, if you're aware of these. In a hospital, in the nursing staff, in this healthcare system, the nurses staff aides receive the lowest wages per hour, $8 versus 4 times more, $24 per hour received by, 3 times more received by the registered nurses, $8 and $24 per hour. So you must take the weighted average, $8 for the 50 nurses aid, $15 for the practical nurses, 50 are practical nurses. So 50 plus 50, 200 minus 50 plus 50 plus, and so the mean wages, because you are taking the weighted mean, weighted towards the nurses' aides and the registered nurses, so you do not make a mistake, the average wages approximately equals $12. The same thing here, the Split Rail Fence Company sells 3 types of fence to homeowners in suburban Seattle, and grade A costs this, grade B costs this, and grade C costs. Again, you have to take the weighted average of all these numbers depending upon what the grade is. Okay. So there are 2 more problems on these, 2 or 3 more problems, I guess. But I'm pretty sure those stuff, the standard deviation, sample variance, and all these that we're going to cover in the next part of this video. So weighted mean, we have completed the mean and kind of clarified some problems why we take the weighted mean. The next thing is the median. Remember, in mean, you're taking all the values, your mean deviation is 0, but because of you have some large observations here, some small observations here, I was telling you the arithmetic mean can be sometimes a biased estimate. So properties of the median. Median. The median, the word itself, and I'll show you this in Excel when we do these problems in Excel, median itself represents a very nice way of standing in the middle. Going back to that income example, it is kind of like the midpoint where you are ranking people's income quite at the midpoint. So it gives you a much better way of handling a household income level, or let's say company's income level, or I would say the median GPA for students than the mean that we just covered. Like the mean, it can be covered, can be computed for ratio level, interval level, and even ordinal level data. The ranking system, the median is very important. Unlike mean, it is not affected by extremely large or smaller values. You will see this. It can be computed through a frequency distribution. Why is it not affected? Because median is towards the middle. And again, I go back to that census household income level data again. From now on, ladies and gentlemen, after having taken a stats class, try to take the median income level, the median age of a population or a sample, something like a median rather than the mean. You can compute the weighted if you have the weights given, but if you do not have the weights given, that how many of the sample are earning this much income and all these, it's better to represent the median income level of a population on a sample. Okay, please bear this in mind. Median gives you a much better idea where it's a much better central tendency. I would not say all the time, but most of the time where your median level is concentrated is giving you a much better representation of your values from this population or from the sample. So medians are easy to calculate when you have an odd numbered series of observations. What do I mean by odd numbered series of observations? 1, 2, 3, 4, 5. You just take the middle value, which is 19, which is actually you have to arrange it in ascending order. That means smallest to be highest. So 19, 21, 19, 20, 21, 22, 25. 19, 20, 20, 20, 25. So 21 would be the median. Let's see an even numbered combination, 76, 73, 80, 75. Again, arrange them in ascending order, 73, 75, 76, and 80. Median is 75.5. Why? Here, you cannot take the middle value. You take the sum of these two and take just a plain average. Yes, that is the median. That is going to give you a median. Median may not be within the sample. Okay, just like the arithmetic mean. 75 plus 76 divided by 2 is 75.5. So I'll arrange these just for our clarity. These are the numbers given to us. I'll arrange these. I actually arranged these when I was kind of writing these numbers down. This is what is given to you. You find the median. Very quickly, I will, this might be a problem in the exam. I'll write this. I always feel comfortable writing them in a column manner rather than in a horizontal manner than the textbook examples sometimes present them. Okay, arrange them in. Okay. Please. Let's cross. So sometimes one. One. That's better way of doing it. 3. 3. 557, 5, 9, 9. When you do this, please make sure without any rush that these are the same number of observations: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have arranged them. As you can see, these are 10, so even numbered observations. So in odd numbered, you can just leave the one in the middle as the median. But in even number, there's a problem: 1, 2, 3, 4, 5. And here are four numbers, four observations here. And then 5 plus 7, here are four observations here. So median would be kind of come in the middle, leave four observations up, four observations down, and median would be 5 plus 7 divided by 2, that's 6. So 6 is not here. 6 can be the median. So middle level of central tendency, middle rank. I usually, this is conventionally when I do my research or anything, I actually pull up the mean, but more importantly, I look at the median values, and then we obviously have to look at what is known as the variation, something we are going to take up next. Now, the last measure of central tendency, the mode, I don't actually give you a lot of problems on mode. The mode is like a value which appears the most. It's interesting, like if you have a frequency distribution, and remember in chapter 2, you know how to pull out the frequencies for each class intervals, and how many are the most, that becomes the modal number. This distance in miles between exits, 1 mile exits, are the modal numbers because the most. And from a bar graph, it is very clear because you have the highest level of the frequencies, how much numbers are the most, that's mode. One thing about mean, median, and mode, and I'm going to show you Excel problems on these later, as I said, is if they are kind of coincidentally at the same location, we have a very nice bell-shaped distribution. We call it a normal distribution, more on it later, but it says it's a zero skewness, zero cut, almost zero kurtosis, and the variance is very less. You have a very symmetric data. Whereas if you have too much of the mean in here, but the mode and the median is slightly, the data is a little bit concentrated to there, we say it's a positive skewness because you draw the data here with a long tail. When you put on a nice line graph, you can put these like this. You take it here and take the distribution. You have a huge tail on the right-hand side. The median and the mode falls too much to the left, but the mean is slightly to the more to the right. Whereas if the reverse happens, the mean is more to the left, and the mean and the median and the mode falls to the right of the mean. The data is obviously not symmetric. It's actually skewed to the left because you will have a little bit of tail in the left. By these, I just mean, and sometimes it's much more easier to graph these. So let's see if I can put it up on the Zoom whiteboard here for you guys to understand, because this will be interesting later. To conclude, to give, I mean, this is a basic statistics class. You can give a brief conclusion about your data. In fact, even in chapter 2 frequency distribution, you can do this with a histogram. This will be skewed to the left. It's not exactly depiction of what I wanted to mean because my hands just got. That's the way you want it to be. Skewed to the right. Somehow. So most of your more too, but I'm just putting this. Whereas this is skewed to the right. What is more important than skewness is not symmetry. Another way of looking at the opposite picture. this is how you can also draw that if you want. So that's simple. It becomes more symmetric than I really believed it to be. We wanted it. Move to the left. More symmetry. Symmetrical means everything is kind of balanced together, as you can see in a bell-shaped distribution. And here, right? Okay, so that leaves us with one section still left, which is the measure of dispersion. I didn't want the video to be too long because the measure of dispersion, we will go over variance, standard deviation. Again, the population variance and population standard deviation is important, and we will do a few problems related to that.